In this video, we are going to begin discussing integration, but we're going to do so by first talking about area and then estimating finite sums. So what we want to do is we want to try to find the area under the curve, and we'll explain exactly what that means here in just a few moments. But before we do that, just a reminder that in the first part of calculus, we estimate the slope of the tangent line using the slope of secant lines. And then, via limits, we can calculate exact values of derivatives. So here what we're going to do is we're going to do something similar. We're going to estimate the area under the curve, and then eventually we will take a limit of these estimated area under the curve, or areas under the curve, and that will help us calculate the exact area under the curve. So in this video, really what we're going to focus on is we're going to estimate the area under the curve, and we're going to do that via this intro example. So our example here is going to be to approximate the area under the curve y equal to x squared for x equal to 0 to x equals 1. What does that mean? Let's draw the picture real quick. This is the point 1, 1. And we have the, we have the point 0, 0 here, and we have our function y equal to x squared. And the area under the curve between x equals 0 and x equals 1 is the area below the curve but above the x-axis from x equals 0 to 1. So we want to calculate this area here, or estimate it at least. How do we go about doing that? Well, that's what we'll see now. I'm going to first draw this picture quite a bit bigger. So that we can see what's going on. And here will be our y-axis. Here's our x-axis. And y equals x squared will look something like this. So here's how we're going to do that. We're going to first estimate the area under the curve using something called R2, or we're going to calculate something called R2, which is to use the right-hand method with two rectangles. Now, how do we do this? What does all of that mean? What are we actually doing? Well, we're going to estimate the area under the curve here by calculating the area of two rectangles, right? It's really hard to calculate what this whole area is, so we're going to estimate by calculating the area of rectangles. And we're going to first break this up into two rectangles. And to do that, we're going to break up our horizontal distance here evenly into two pieces. And we're going to calculate the area of two rectangles. The two rectangles are here. So we're going to calculate this area plus this area, add up all of that, and use that as an estimation for our area under the curve. As we see here, that's not going to be a great estimation, or we're going to get a value that is much bigger than our correct solution. But let's go ahead and start with how to do this. Now, notice that the width here of each rectangle is 1/2. The height of each rectangle is the function evaluated at the endpoint. And I said the right-hand method because we found the height by picking the height to be the right endpoint of each of these intervals. So R2 here is the area of the first rectangle, so I'm going to call that A1, plus the area of the second rectangle, which we're going to call A2. Now the width of the first rectangle is 1/2, and the height of the first rectangle is 1/2 squared. Why is it squared? Well, that's the value of our function, right? Our function is x squared, so the height of the function at that point is x, which is 1/2 squared. So we get 1/2 squared. Plus, let's go ahead and calculate the area of the second rectangle, where our width is 1/2 and our height is 1 squared. All right. So we get 1/2 squared is 1/4 times 1/2 is 1/8 plus 1/2. And all of this put together is 5/8. Okay, we're going to do something very similar here and calculate R4. Now, what is that? Well, that is the right-hand method with 4 rectangles. Let's go ahead and draw the picture of that. Okay, this time we're going to break it up into 4 intervals. So our width here is going to be 1/4. And the height of the rectangles is again the height of the function on the right-hand side of each interval. So let's go ahead and calculate that. Well, this is A1 plus A2 plus A3 plus A4, which is just the area of each of our rectangles here. And the width of each of the rectangles is 1/4 times the height. All right, so this is going to be 1/4 times 1/4 squared plus 1/4 times 2/4 squared, or in other words, 1/2 squared. And the area of the third rectangle is a width of 1/4 times the height of that rectangle, which is 3/4 squared, plus 1/4 times 1 squared for the last rectangle. All right, so this is 1/4 squared, which is 1/16 times 1/4 is 1/64. 1/2 squared is 1/4 times 1/4, so this is plus 1/16. Plus, 3/4 squared is 9/16 times 1/4 is 9/64. Plus 1/4. All right, if we add up all of that, this is 1/64 plus 4/64 plus 9/64 plus 16/64. 16 plus 9 is 25, plus 4 is 29, plus 1 is 30/64. And that is our estimation of the area under the curve using 4 rectangles and the right-hand method. Notice that this area is much closer to the true area than up here, right? If I drew this same picture on here, we're getting this kind of a picture. Now, so we get a lot closer to the true area under the curve. And we've been able to cut off this piece and this piece now when we do 4 rectangles instead of 2. And then we can continually get better and better and better estimations by picking smaller widths here, or in other words, more rectangles. And that is the idea to estimating the area under the curve. We just make more and more rectangles, and we get closer and closer to the area under the curve. Real quick in this video, we are going to do a similar calculation, but with the left-hand limits. So let's now calculate or estimate the area under the curve using L2. This is the left-hand method using 2 rectangles. Now, what is that? Again, we have our function here. Using 2 rectangles means we break this up into just 2 intervals. But now we want to use the left-hand side of each interval as the height. Well, the left-hand side of the first interval is just 0, right? We plug in 0 into the function and we get out 0. So our height is 0. And now we use the left hand on the second interval, and we get this rectangle here. So L2 is the width 1/2 times the height, which is 0 squared, plus the second rectangle, which is 1/2 times 1/2 squared. So we get 0 plus 1/8. And we see that we're missing a lot of the region here, so this is not a great estimate. But what can we do? Let's calculate L4 now. Let's put in more rectangles. So how do we do that? Well, let's break this up into more intervals now. Our first interval here, using the left-hand method, will have, again, a height of 0 and a width of 1/4. Our second interval is now a height of 1/4 squared times the width of 1/4. Our third interval is now a height of 1/2 squared times the interval of 1/4. And our fourth interval is now a height of 3/4 squared times a width of 1/4. And so, again, we can call it A1 plus A2 plus A3 plus A4. Calculate those areas, and we get 1/4 times 0 squared plus 1/4 times the left-hand endpoint here. The height of the second rectangle is 1/4 squared, plus 1/4, the width here, times its height, which is 1/2 squared, plus 1/4 times 3/4 squared. We put in all of this, we get 0 plus, 1/4 squared is 1/16 times 1/4 is 1/64. 1/2 squared is 1/4 times a fourth is 1/16. Or in other words, 4/64. Plus 9/16 times 1/4 is 9/64. And we end up with 14/64 as our estimate of the area under the curve using the left-hand method and 4 rectangles. So what we can say then is that the area is somewhere between our lower estimate of 14/64 and our upper estimate of 30/64 when we found the R sub 4. And again, in both cases, we can keep doing more rectangles, so getting a higher value, either R sub 8 next or L sub 8 next, in order to estimate the area under the curve to a closer approximation. Those calculations get a little bit messier, but you can see the idea here. And that is where we will end this first video.